Let's talk about one of the most important supervised learning techniques out there, classification. Welcome to this video on classification. My name is Kevin Fiesel, and I'm the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. This video is the start of a brand new series, and we'll be talking about classification algorithms over the next several weeks. What I'd like to do in this video is give you a brief overview of what classification is, talk about some of the benefits of classification, and take us through one of the simplest classification algorithms out there in CART. Let's go to the classroom and dig in. This series is based on a presentation that I've put together entitled Keeping It Classy, Designing a Great Classifier. In the description below, I'll have links to the slides that I use when delivering this talk, demonstration code I use, and links to additional resources. Usually, I only have about 60 minutes to impart as much information as I can, but with this series, we'll take it a little slower and talk through the ideas at, shall we say, a slightly more leisurely pace. But don't get me wrong, there is a lot to cover, and cover it we shall, so let's get started. The first question that comes to mind is, what is classification? It's a fair question after all. Classification is a technique involved in supervised learning. This, of course, brings up the next big question. Well, what is supervised learning? It's a good thing I have the answers here, because that's exactly what supervised learning is. Our goal here is to train a model. To do so, we start with a dataset. To this dataset, we apply an algorithm, a set of mathematical formulae. The output of this combination is a model, and we call this process training the model. Now, there are two basic varieties of dataset that we can use, and the split is on whether we already know the answer or not. Let's suppose I'm trying to build a model that can tell me the score of a baseball game given some set of inputs. We could speculate as to what those inputs ought to be, but it doesn't really matter here. What does matter is the answer to this question. For each set of inputs, do we also have the final score of the game? If so, we call that final score a label, and all of the other columns features, and we have a supervised learning dataset. My dataset includes examples of what final scores were, and so we could generate predictions about what we think the final score will be given some new set of inputs. By contrast, suppose we don't have the final scores. We don't have labels, but we do have a set of features. Now we have an unsupervised learning problem. We don't actually know the answer in terms of how many options there should be, what exactly those answers look like, or even how closely we'll be able to hew to those answers. The image here still describes both supervised and unsupervised problems, but as you could imagine, getting a reasonable answer is a lot harder with unsupervised learning. That's why supervised learning is so common in business problems. It provides us a way of getting reasonable, verifiable information for business users. There are good use cases for unsupervised learning, but the whole process around not just verifying answers, but even making sure you're doing it right, it's a lot trickier. Fortunately, we are going to stay on the supervised learning side of the house. Incidentally, you might be asking yourself if there are techniques other than supervised and unsupervised learning. And yeah, there are. One of the most common of these other techniques is called self-supervised learning. The idea with self-supervised learning is that your model starts with some bit of known good information and then generates the next step in the process from that information. Then, taking that known good info plus its first step as the new input, it generates as its output the second step, and so on until it completes. If this sounds at all like what you've heard of with large language models, you're right on the money. The model is taking a series and generating a likely token given the rest of the series, and then repeating that process until it completes. Let's get back to supervised learning though. Here's an example of the kind of data we might see with supervised learning. In this case, we have a set of input features. We also have an output that represents something of interest to us. In this case, the output column is our label, and it takes on one of two values, either a 1 or a 0. So this gets me to classes of supervised learning techniques. There are 3 popular classes of supervised learning technique. The first is regression. Regression answers questions around how many or how much. How much do we expect a new graduate to earn? How many licks does it take to get to the center of a Tootsie Roll Pop? Those are the sorts of questions we try to solve with regression. The answer, by the way, is 3. The second is recommendation. Recommendation answers questions around what next. I like these types of movies, so what should I go see in the theaters? The third type is classification. Classification answers questions like which of these categories is the best fit for my blog post? Which treatment group does this patient belong in? As you can see, these 3 answer quite different problems, and part of knowing that you have a classification problem is by listening to the business sponsor, or whoever is giving you the problem to solve and hopefully the big sack of money to solve it with, listening to the kinds of questions they are asking. Now that we've gotten that out of the way, let's talk about classification itself. The most common form of classification we tend to deal with is 2-class classification. In the case of this image, we have class 1 and class 0. But you can also think of this as true and false, yes and no, win and lose, more taste and less filling, whatever. We have 2 answers from which to choose, and we must choose one of those 2. By contrast, multi-class classification has a couple of possible meanings. The first meaning is our label may take on one of a series of values. So let me give you a few examples of this. One common example is choosing the category of a blog post based on the text. This blog post belongs in humor, this one in news, this one in science fiction. Another common example is choosing a product category when you're listing a product in a marketplace. My product is a cell phone case, so I can classify it in the cell phone cases and accessories category. Sticking with business-related examples, perhaps I have an advertising campaign and I want to estimate how profitable the campaign will be. If I'm trying to estimate how much profit the campaign will earn me, that's a regression problem. But that problem might be hard to do, especially with a limited data set. Therefore, we may condense the problem down to one of a few options, maybe very profitable, somewhat unprofitable, and very unprofitable. Now I'm asking, to which class does this particular campaign belong? And that is a classification problem. But there's actually another possible meaning to the idea of multi-class classification, and that is, not only do I have multiple classes, but I may also choose more than one. In the blog post example, most software for hosting blogs lets you define a set of categories, and you can choose multiple categories from that set for each post. For the sake of keeping things fairly simple though, I'm going to focus on the first definition of multi-class classification, where we choose one class from a set that includes more than 2 classes. The next thing I'd like to talk about before we get into our first classification algorithm is how do we know how good our model is? I'm going to talk about one measure today in accuracy, but if you're planning on throwing your mice in a fit of rage that, I'm only talking about accuracy, well, I do promise to dedicate an entire video to the topic of measuring model quality, so please be a little patient. The basic idea of accuracy is as follows. We are going to take the sum of correct answers and divide it by the total sum of answers. This will give us a value ranging from 0 to 1, where 1 is perfection and 0 is perfectly wrong. So alright, let's now talk about our first algorithm, classification and regression trees, or CART. The idea behind CART is deceptively simple. It's a decision tree, or a series of if-else statements. If the database size is less than 50 gigabytes, and the memory usage is less than 32 megabytes, and the file count is less than 10, something. If the file count is greater than 10, well, something else, and so on. We build out these if-else statements in such a way that we provide answers at the end. In our case, we're looking for a specific class of result. But CART does more than classification. It is in the name after all, classification and regression trees. You can use the same algorithm to solve both classification and regression problems, which is pretty neat. But we'll focus on the classification side of the house today. Let's say that we plan to use CART on our dataset, and the goal is to generate results for the output column, which can take on a value of either 0 or 1. There are 3 big questions we should ask ourselves. First, which feature should we split, and at what value? In the decision tree example, my first split was database size at 50 gigs. But how do we figure out that database size is the right feature to split, and how did we get that 50 gigs was the right splitting point? Second, how do we decide when a branch shouldn't split any further? In other words, could I have some indeterminately large tree that encompasses all possible cases? I might be able to, but that's probably overkill and it's liable to overfit the data. In other words, I would be training to the peculiarities of the dataset rather than the broader problem at hand. And so the trained model would make assumptions based on the happenstance of a subset of the total universe of examples. Third, which label value should we predict at each terminal node? And a terminal node is the final node in a sequence. If a database size is less than 50 gigs, and its memory usage is less than 32 megabytes, and its file count is less than 10, is that going to be a 1 or a 0? So let's take these in Quentin Tarantino order, starting with the second, going to the first, and implying the third along the way. We can use stopping rules to prevent splitting a branch any further. There are a few common stopping rules that libraries like scikit-learn have built into their CART implementations. Examples of these include, first, we stop when we have fewer than a minimum number of cases for a given node. Let's say we want a minimum of 10 cases, and we have 8 in this node. In that case, we would stop right there. If we still have 15, we can break things out one more time. Stop when all cases are of the same label. If all of our cases have an output value of 1, it doesn't really matter how many cases remain. No matter how we split the data, everything will have an output of 1, so just stop right here. We could also stop after reaching a certain depth or a node count. Each level of a tree requires more memory. Each level also requires more cases to be meaningful and limit the risk of overfitting. So let's now talk about how we decide on the column to split and at what value. This is an example of something called a feature importance graph, something we can generate in some of the classification algorithms we'll talk about in this series. In this particular case, we can see that based on the data we have currently available to us in a given node, age is the most important feature, followed by cholesterol, and with a few other features showing somewhat less importance. We always split on the most important feature, meaning that, in this case, we would split on age. Then we want to pick the value of age that best hews to 2 separate properties. First, we want a value that best splits the data between its classes. If I can get a value of age where 95% of the results on the left-hand side are in class 0 and 85% of the results on the right-hand side are class 1, that's a great split. If we cannot cleanly split the data between classes, we at least want a relatively balanced split of results. So if we have 1,000 cases, we want to pick a value of age that leaves the left and right-hand sides somewhere in the neighborhood of 500 results. We perform this feature importance and splitting exercise for each node until we reach a stopping rule, giving us a final result. Along the way, CART has a few useful properties we can take advantage of. First, it does not expect the data is in some given distribution. We don't need to assume the data is in a normal distribution, or log normal, or Poisson, or anything else. Some algorithms do expect the data to be in a specific distribution and may generate incorrect results if you use them in breach of that promise. Second, outliers do not affect CART very much. Outliers are, by their very definition, uncommon and generally not related to the mass of data. In those cases, outliers typically go off in their own terminal nodes, leaving the inliers to their own nodes. Third, CART supports testing and validation of results. In other words, I can perform cross-validation with CART, splitting my training data some number of ways and training with all but a subset of that data. I can then check the results of my validation set versus the remainder of the training set and repeat that process for each subset of my training data. This lets me know how volatile my results are. If my training data changes slightly, how much does the model change? Test data, meanwhile, is data that the model has not yet seen, and we use it to gauge how good the end result is. Fourth, we can reuse a given variable in the same tree with cart. If I have age as the topmost variable, it may turn out that age becomes useful again deeper in the tree. Not all algorithms allow for feature reuse like that, so it is a notable property of cart. We've done a lot of talking about cart, so let me jump into a demo and I'll show it off. Let's dig into our first demo here. All of these demos are in Jupyter Notebooks to make things easier to try out. Incidentally, I also have a requirements file, so that way you can see exactly which packages I'm using. Across all of the demos, we are going to use a few libraries. We will need scikit-learn, NumPy, Pandas, and Matplotlib as core libraries. After that, we'll install XGBoost and LightGBM. These are the only two algorithms we won't use straight out of scikit-learn. That fact alone should give you an idea of how powerful the scikit-learn library is for classification problems. Finally, we'll install GraphViz to visualize trees. One important thing to note is that after you install GraphViz, you'll want to make sure the installation folder is in your path. Otherwise, you will get an error when trying to run GraphViz. Also, this pip package does not install all of the GraphViz library components. If you're running on Windows, there is a separate executable that you'll need to install. I can drop a link in the show notes below so that you can grab it. Now that I've got everything installed though, let's switch over to the first Jupyter Notebook. This notebook will give us an idea of how cart works and will also serve as a pattern for pretty much every other notebook in this series. We will start by importing a few libraries, NumPy, Pandas, and various bits of scikit-learn. Next, we create a classifier that I'm going to call CLF. In this case, we will use scikit-learn.tree.decisionTreeClassifier to do this work. I'm going to set the max depth to 4, meaning that the tree can be no more than 4 decision points deep. That means there may be no more than 16 terminal nodes in a filled out tree. Incidentally, if you do not set this parameter, the tree can get much deeper, but it won't really improve accuracy much as we're more likely to overfit the deeper the tree goes. The data set we will focus on for the first part of this series is a heart attack data set I originally grabbed from Kaggle. Let's take a peek at what it includes. We can see that there are 13 features and 1 label, with output being the label. Some of those features are self-explanatory: age, cholesterol level, sex. But most of these are going to be a bit confusing to people without subject matter knowledge. I won't spend a lot of time talking about these features because ultimately we're using this data set to learn against, not to draw interesting conclusions or dig into the nature of heart attacks. For the sake of simplicity, the outcome of 0 is a good outcome, no long-term heart disease. By contrast, an outcome of 1 indicates long-term heart disease. We're going to use the other features to see if we can draw any likely conclusions about who ends up without long-term heart disease and who ends up with long-term heart disease. One thing I will point out is this is a very comfortable data set, in the sense that all of the features are numeric and we aren't missing any data. That's a rarity in the real world, but it does make our analysis that much easier, as I can get right into it rather than spending a lot of time cleaning up the data. But having this data be entirely numeric is important because scikit-learn requires numeric inputs for all classification algorithms, and the same will apply for XGBoost and LightGBM. One other thing that I will point out is there are only 2 values for outputs, as we can see if I drop duplicates. I have 0 and I have 1. There is no other outcome, so we are in the world of 2-class classification. The next step is to split out features from labels. I'm going to put all of the features into a variable called x, and the labels in a variable called y. Those names are by convention, similar to using CLF for classifier function. After breaking out features from labels, I'll call the train test split function in scikit-learn. I'm going to break out the dataset such that we have 70% available for training and 30% available for test. There are 303 rows in total, so I would expect approximately 210 training rows and 90 testing rows, give or take a few. I think I've explained my philosophy on train test splits before, but just in case, here's the really quick version. In an ideal world, almost all of our data would go into training so that we get the most variation and the broadest patterns we can possibly see. That way, the real world is a little less likely to confuse our trained model, as it has to rely solely on the subset of all real-world data that we're able to feed it in our training dataset. But we also need to balance this out with the need to have enough variety in the test dataset that we're confident we have hit most or all of the major cases. This is a real tension, and there isn't a clean and perfect a priori outcome. We default to something like 20 or 30% of data being test data as a rule of thumb because it does act as a reasonable starting point. If we did a detailed analysis of the distribution of input features for cases with heart disease versus cases without heart disease, we might come up with a more precise ideal number for testing. But because our initial dataset is only 300 records, I doubt we would land at a drastically different set of values. So I think in this case, it's fine to stick with the rule of thumb. If we had 1 million records, that would be a different story, and I would expect our test dataset could be a significantly smaller percentage of the whole. Next up, it's time to perform classification. I'm going to run the fit function for our decision tree, sending in the training features and training labels as the two inputs. That gives us a trained model that I've reassigned to CLF. In order to see how well we've done, we've held back the test dataset. I'm first going to predict what the model thinks the outcome should be. Those values are the predicted values. Then we'll run scikit-learn's accuracy score function to compare the actual outcomes versus our prediction. In my notebook notes, I mentioned that we get the right answer about 75.8% of the time. When running the notebook, because I don't have a fixed state for the training process, that actual number may be a little different, but it's consistently been in the 73 to 77% range over the few dozen times I've run this notebook over a couple of years. So I'm pretty confident CART will get this right about 3/4 of the time. The last thing we're going to do is visualize the classification tree that we've built. To do that, I can use the GraphViz library and scikit-learn's export GraphViz function. I'll send it the trained model, my set of feature names, my 2 classes, and a few attributes to make the results a little nicer looking. Then I can create and display the graph. This tree will probably look a little different based on the roll of the dice. That said, we often see one of 2 features at the top of the chain, either the thallium stress test result or age. Boxes that are in orange are paths less likely to lead to heart damage, whereas boxes in blue indicate paths more likely to lead to heart damage. Any boxes in white have a near equal split between heart damage and no damage cases. Also, the number in each box is the Gini coefficient, which is a measurement of how skewed the distribution of results is. If the Gini coefficient is 0.5, that means a near equal split between heart damage and no heart damage cases. If the coefficient is 0, that means 100% of the cases fit into one bucket or the other. Ideally, what we want to see is our terminal nodes have a Gini coefficient near 0 and a relatively large number of samples, as that gives us confidence in our results. The higher the coefficient, the more likely we are to miss on our answer. Incidentally, digging through the tree results can also give you a good idea of areas to circle back on. If we have a situation in which a terminal node is a near 50-50 split, we could investigate further. We could see if adding another level would break the split, or maybe see if there's a difference in that particular subset of the data. We might even go back to the original data source and see if the labels were correct, or check with subject matter experts to learn if there are any other features we might be able to incorporate in order to separate those cases. Sometimes, however, we may just need to recognize there can be ranges of uncertainty, and we may well have stumbled upon one. And that was CART, the first classification algorithm we're going to look at in this series. CART is extremely useful, which is why I wanted to lead off with it. But it's definitely not the only useful algorithm, so we'll learn about quite a few more as we go along. In the next video, I'll introduce you to the concept of bootstrap aggregation and random forests. We'll have links and show notes in the description below, and until we see each other in the next video, take care.